Hello students, just a quick going over of quiz 1. Okay, question 1, state whether the following sentences are simple or compound. If they're compound, write out the simple component sentences. Question 1, this sentence is simple. Okay, to remind yourself why this is so, look back to page 23 of the text, right? Reminds you of what simple and compound is. It's important to realize that rather complicated looking sentences may still be simple in our sense of the word. Right, the subject may be, well, you can read through this, page 23, last paragraph of page 23 explains why number 1 is simple. 2 and 3 are both compound. Why? A compound sentence is one that contains another sentence as a component, or contains at least one other sentence as a component, right? One sentence contains another sentence as a component if any part of it makes a complete sentence by itself, and you can replace this sentence, as you can for 2 plus 2 equals 4, that's a sentence. If you can replace that with any other sentence and the result is a grammatical sentence, then yes, the highlighted part here does count as a component sentence of Andrew believes that 2 plus 2 equals 4. So this is a compound sentence, and the component is 2 plus 2 equals 4. Quite a few people lost a point for writing Andrew believes that, right? That is not a component sentence, right? Andrew believes that this, right? This is a sentential operator. Sentential operator is an expression containing blanks whereby if you put any sentence into the blank, you get, as a result, another sentence, right? So blank or blank is a sentential operator, 2 plus sentential operator, blank and blank. Those things for which we have symbols, those are all sentential operators. But anyway, this is not a component sentence. Sentential operators are not component sentences. They're a different kind of element. Number 3, Dan and Uchenna are Americans. This is a compound sentence, right? A compound sentence is a sentence which logically contains one or more sentences as components, okay? A sentence can logically contain another sentence as a component if it either literally contains another sentence as a component or can be paraphrased such that it does then literally contain other sentences as a component. Few people ask me why this isn't simple, because it looks like Dan and Uchenna are married, right? But Dan and Uchenna are married, as I explained in the lectures. The predicate are married, right? Are married. This states a relation, right? And the attempted paraphrase fails, right? So it is not the case that Dan and Uchenna are married. It is not the case that that sentence, Dan and Uchenna are married, can be paraphrased as Dan is married and Uchenna is married. Why not? Because one sentence only paraphrases another sentence if they are both true in the same situations and false in the same situations, right? And it's possible for Dan and Uchenna, it's possible for Dan is married and Uchenna is married to be true when the sentence Dan and Uchenna are married is false. In which situation? When we're both married to different people, right? But this is not, this sentence 3 is not the same as that, right? This is not relevantly like that sentence, in that the predicate here is different. Dan and Uchenna are Americans. The predicate is American. This predicate applies individually to the two subjects. So here we have a compound subject, and this is logically equivalent to, that is, sentence 3 can be paraphrased as Dan is American and Uchenna is American. The truth conditions of this original sentence as stated and the paraphrase are exactly the same. The truth conditions for the two sentences are the same. It's a successful paraphrase so therefore, since this sentence can be paraphrased into a sentence which does literally contain another, in this case, 2 sentences as components, it is a compound sentence, right? And what are the simple components? The first one is Dan is American. The second one, Uchenna is American. Okay, that's where most of the points were lost on those first three. You did overall quite well on 4, 5, and 6, right? So just quickly, right? What's the major operator? Is it this wedge or the dot or this dot, right? Those are the operators. The capital letters are centential constants. And the way to figure it out, right, just say you hypothesize, you suggest maybe this wedge is the major operator. Well, what's the rule for forming formulas with the wedge, right? You've got to have a legal formula to the left and a legal formula to the right, right? That's the rule for all these two-place ones, all these two-place operators. You build a new formula so long as, right, so long as you have a legal formula on each side, right, where the blanks go, right? So wedge is blank, wedge, blank. That's how you build things. Okay, so would this be it? Is this wedge it? No, because, this string of symbols here, bracket, brackets, A, open parentheses, A, that is not a legal formula, right? Any parentheses you open, you have to close. Similarly here, B, close bracket, dot, C, close bracket, dot, D, that is not a legal formula, right? Same problem if you try this one. Is this the major operator? No, because C bracket dot D, not a legal formula, right? Similarly here, you've got these two brackets go together, but this open bracket isn't closed, not a legal formula. Only with this dot here, and that's the right answer, is the last dot, as most of you got. This is a legal formula, right? You've got the same number of open and closed brackets, and D by itself, that's legal. Same reasoning will get you to that the wedge is the major operator, right? This string of symbols here, actually just to here, that's the legal formula. This bracket goes with that, sort of unnecessary. Similarly, 6, okay, where mistakes were made, it was in number 6 here. That's where most points were lost in this part 2. Okay, so remember the negation rule, right? So you got a negation at the start of the formula here. So the question is, what is being negated? What formula is being negated? Well, a negation, right, is a one-place sentential operator. What's the rule for constructing formulas with negation? It's just you got to put a legal formula here, and you get a new formula, which will be a negation. So what am I negating? What am I negating here? Well, in the actual 6, right? Remember the right-hand rule from the lectures. You put imagine this highlighted blue. That's my hand over it, right? And you move your hand to the right. You go, okay, I've got an open bracket. I've got an A. That's not a legal formula. Open bracket A, right? Only when I get to the only when I've closed this bracket do I get the complete formula that's being negated, and I get biconditional B, close bracket. Okay, that's a complete formula. The whole thing in blue, that's a complete legal formula. That is what is being negated. That means that first I built the biconditional. I did A biconditional B, and then I negated that, right? So the last operation, last step in the order of construction of the formula is the negation. The negation is the major operator. Compare that to this formula down here, right? Here, I do the right-hand rule, and look, when I get to A, since there's no open bracket, it's A, which is the first legal formula I get. Doing the right-hand rule, that is covering up everything after the negation. Okay, so when I get to A, I say, that's what's negated. So the major operator of this guy is the biconditional, right? This is made by first negating A, and then second, I made a biconditional with not A on the left and B on the right.